Hello, welcome. In this lecture, we generalize the concept of vectors and introduce the notion of vector spaces in an abstract sense. We will discuss the following topics in this and the next week. Vectors in Rn, vector spaces, vectors in abstract or general spaces, subspaces of vector spaces, spanning sets and linear independence, span of a set, basis and dimension of a vector space, dimension of subspaces, row space and column space of a matrix, rank of a matrix, and coordinates and change of basis. Let's begin our discussion of vectors in Rn. Definition. For a natural number n, we define the set Rn is a set of all list of numbers written in a column form enclosed by square brackets, where each x, I, is a real number. For example, x sub 1, x sub 2, all the way up to x sub n are all real numbers. For example, the ordered pair written in a column form 1, negative 2 is an element of the set R2. The ordered triple with components negative 3, 4, 1 is an element of the set R3. And this list with 5 components negative 2, 4, 0, 12, negative 3 is an element of the set R5. The objects in Rn are called vectors, more specifically geometric vectors. In this lecture, we will generalize this concept of vectors and explore vectors other than the geometric ones. In other words, not every vector looks like an n-tuple. Definition. Let x and y be two vectors in Rn with components as shown. We say x equals to y if and only if x sub I equals to y sub I for all I equals to 1 to n. Meaning that the first component of x is equal to the first component of y, the second component of x is equal to the second component of y, and so on. The sum of two vectors in the set Rn and the scalar multiple of a vector in Rn are called the standard operations in Rn and are defined as follows. Let x and y be two vectors in the set Rn and c be a real number. Then the sum is denoted by this symbol and the scalar multiple is denoted by this symbol are defined as these two formulas. So the sum of the vectors x and y is obtained by simply adding the first components of the vectors and the second components of the vectors and so on. In short, the first component of the sum is the sum of the first components of the vectors. So on. Similarly, the scalar multiple is obtained by simply multiplying by every component of the vector x by the constant c. Clearly, the vectors x plus y and cx are in the set Rn, since they have the n components. And they are real numbers. Definition: the element in Rn with all the components equal to 0 is called the zero vector in Rn. For example, this vector is an element of R2 space, but this zero vector is an element of R3 space. We observe that the 0 in R2 and the 0 in R3 are not the same zero vectors, since they have different number of components. Definition: if x be a vector in Rn, then the following vector is called the negative of x, which is denoted by negative x, which has components the negatives of the components of the vector x. For example, if x is a vector with components -1, 4, 3, 2 in our 4 set, then the negative x has components +1, -4, +3, and -2. Clearly, this vector is also in the set R4. Theorem: properties of vector addition and scalar multiplication in Rn. Let x, y, and z be any vectors in Rn, and c and d are real numbers, then x plus y is in also the set Rn. This property is called the closure property. It means that the set Rn is closed under addition. If we take two vectors from the set Rn, their sum is also in Rn. Property 2. X plus y is equal to y plus x. This is called the commutative property of Rn. It means that the addition is commutative. Property 3. X plus y plus z is equal to x plus y plus z. This property is called the associative property of Rn. It means that the vector addition is associative. We can add the first two vectors, then add the third one, or we can add the last two vectors and then add the first vector. Property 4. X plus the zero vector is equal to x. It's true for all x in the set Rn. This property is called the existence of additive identity. The vector 0 is called the additive identity element in the set Rn. Property 5. X plus the negative of x is equal to the zero vector. And this is true for all x in the set Rn. This property is called the existence of additive inverse. The vector negative x is called the additive inverse of the vector x. In the previous page, we discussed 5 properties for vector addition. The next 5 properties are all about the scalar multiplication. Property 6. If x is in Rn, then Cx, the scalar multiple of x, is also Rn. and this is true for all C, real number. This property is called the closure property for scalar multiplication. It means the set Rn is closed under scalar multiplication. Property 7. C times the vector x plus y is equal to cx plus cy. This property is called the distributive property. The scalar distributes over the vectors in Rn. Property 8. C plus d times x is equal to cx plus dx. This is called the distributive property. In this property, the vector x distributes over the scalars. Property 9. CD times x is equal to c times dx. This property is known as the associative property of scalars. And finally, we have property 10. 1 times x is equal to x. This is true for all x in the set Rn. This property is called the existence of multiplicative identity property. Let's try to prove some of these properties. The proof of the property 1, namely, if x is taken from Rn and y is a vector in Rn, then their sum is also in Rn. The proof of this property immediately follows from the definition of the vector addition. Property 2. We want to show that if x and y are two vectors in Rn, then the sum is commutative, namely x plus y equals to y plus x. To prove that, let's take two vectors x and y, as shown here from the set Rn. Then we add these two vectors by following the definition of vector addition. Since x1 and y1 are real numbers, we can commute them. So the sum x1 plus y1 here can be written as y1 plus x1. Similarly, the second component can be written as y2 plus x2, and so on. But the second column is in fact, by definition, the sum of the vectors y and x. So it's y plus x. So the proof is over. In a similar fashion, we can try to prove the property 3. To prove that, let's take three vectors x, y, and z from the set Rn. Then we compute the sum x plus y plus z. So here is the vector x plus y in its component form and the vector z in its component form. The sum gives us this single vector here, which can also be written as the sum of the vectors x and the vector y plus z. This concludes the proof of the property 3. So we proved the associative property for vector addition. Property 4. By using the definition 9.1.1, we can write x and 0 vector in this form, and then we can add x with the 0 vector. So we simply see that the sum is the vector x itself. So we prove that for all x in the set Rn, the vector x plus the 0 vector gives us the vector x. Property 5. If x is a vector with components x sub 1, x sub 2, all the way up to x sub n, then its negative has components negative x1, negative x2, negative x sub n. And then if we add the vector x with its negative by following the definition of vector addition, we get the 0 vector. So this property holds true for all x in the set Rn. The proof of the property 6 immediately follows from equation 9.1.1. Property 7. If x is a vector and y is a vector in Rn with components as shown, then we can calculate the c times the vector x plus y, which can be written as the sum of two vectors by following the definition of vector addition. And we observe that the first vector is none other than the vector cx, and the second vector here is none other than the vector cy. So we proved that the scalar c distributes over the vectors. This is called the distributive property. In a similar fashion, one can prove the property 8. Namely, if we have two scalars c and d, then we can show that c plus d times x is equal to cx plus dx. And the proofs of the properties 9 and 10 follow immediately from the equation 9.1.1. In the next theorem, we'll study something called left cancellation property in Rn. Let x and y be two vectors in Rn. Then if x plus y is equal to x plus z, then y must be equal to z. Observe here that we have an x in the left hand side of the equation and x in the right hand side in the equation as well. So if we have an equation like this, x plus y equals x plus z, then y must be equal to z. This property is called the left cancellation property in Rn. Let's have a look at the proof of this theorem. Since y is in Rn, by property 4 of the theorem 9.1.1 we proved earlier, we can write y is equal to 0 plus y by property 4 as mentioned. Then this 0 can be replaced by negative x plus x by property 5. Then by the associative property, property 2, we can move this brackets here. Now by hypothesis, the vector x plus y is exactly equal to the vector x plus z. And by the property 2, the associative property, we can move the brackets from the last two vectors to the first two vector, as shown here. And by property 5, we can replace negative x plus x by the 0 vector here. And finally, by using the property 4 again, we can write the 0 vector plus z is equal to z. So we proved that y is equals to z under the hypothesis that x plus y equals to x plus z. Corollary. Let x and y be two vectors in Rn. Now if y plus x is equal to z plus x, then y must be equals to z. This is called the right cancellation property. Let's see the proof. The commutativity of vector addition, we can write the left-hand side of the equation as in this form. Y plus x can be written as x plus y. Similarly, the right-hand side of the equation can be written as x plus z. And now the result follows from the left cancellation property we just proved a moment ago. So the right cancellation property is an outcome of the left cancellation property and the commutativity for vector addition in the set Rn. Theorem. Properties of additive identity and additive inverse in Rn. Let x be a vector in Rn and c be a real number. Then the following properties are true. Property 1. The additive identity is unique. That is, if x plus y equals to x, then y must be equal to the zero vector. Property 2. The additive inverse is unique. That is, if x plus y equals to the zero vector, then y must be equals to the negative x. Property 3. The real number 0 times a vector x is equal to the vector 0. Observe that the 0 in the left-hand side is a real number, and the 0 in the right-hand side of the equation is a vector 0. Property 4. The c times the zero vector is equal to the zero vector. Property 5. If c times x is equal to the zero vector, then either the c is equal to the real number 0 or the vector x equal to the vector 0. Property 6. The negative of the negative of x is equal to the x itself. And the property is true for all x in the set Rn. Let's have a look at the proof of some of these statements. We are given an equation x plus y equals to x. Since x plus 0 is equal to x for all x in the set Rn, then the vector x in the right-hand side of the equation can be replaced by x plus 0. Now, the result follows from the left cancellation property, as we proved in theorem 9.1.2. Let's try to prove the statement 2. We are given that x plus y is equal to the zero vector. But the zero vector can be replaced by x plus negative x. Now, by the left cancellation property we proved in theorem 9.1.2, we have the following result. Y must be equals to negative x. So this proves that the additive inverse of an element x in the set Rn is unique. In a similar fashion, we can prove the properties 3, 4, and the rest mentioned in the theorem. Please try to have a look in the proofs.